Hello, my name is John Butterworth. I'm a security researcher at the MITRE Corporation. I'm going to talk to you today about some research that my colleagues and I have been working on, specifically in the realm of firmware attacks and defense. I'm going to show you today some vulnerabilities that we found which permit the bypass of UEFI and Windows 8 secure boot technologies. So, what we have here is just what we're going to refer to for a little while as the malware food chain up here, if I can get my mouse there. So here we have the BIOS firmware. This is what boots as soon as you power on your PC or platform. This is the bootloader, which the BIOS hands off control to once it's done initializing all the firmware and the hardware. The bootloader then searches for a valid operating system and boots it up to this point where you're in your OS. Now, as a general rule, when talking about like the platform boot process, rootkits that are able to execute earlier during the boot process are in a position where they can compromise code which executes at a later time in the boot process. Now, way back when, in the olden days of just really a few years ago, it used to be that malware running with sufficient privileges on the operating system could almost trivially overwrite the BIOS firmware and or the bootloader. For example, it used to be that the BIOS firmware was protected by typically nothing more than just a checksum. Nowadays, all systems pretty much are using signed firmware updates, which ensures that only a trusted signed firmware image is allowed to be written to the BIOS flash. However, that can only protect that which is located on the BIOS flash. So, in other words, it provides no protection to areas or boot components that are located outside the BIOS flash, such as a bootloader, which is going to be located on your hard drive or otherwise fixed media. So in other words, it can't prevent things like bootkits or evil maid attacks and such. However, UEFI BIOS, which is the successor to what's known as legacy BIOS or compatible or conventional PC BIOS, implements a security feature called secureboot. Secureboot, when it's enabled, cryptographically validates a platform boot component like a bootloader before permitting it to load and then execute. However, again, secure boot only checks during the boot process. Thus, it has absolutely no way to protect the actual bootloader itself from that initial malicious write. So an attacker can still overwrite the bootloader and insert a bootkit. However, it's relied on for platform security that upon next reboot, secure boot will check and authenticate that image, that bootloader, and deny it the ability to load and execute. So. In summary of secure boot, basically secure boot will verify any EFI executable or just a boot component, if you will, that's found by the UEFI BIOS during the boot process. Now this all depends actually on the secure boot policy. So what we see here is the verification handler. This determines secure boot's actions that it will take on a file that's attempting to load and execute based on the originating location of that file. For example, if it's originating on the boot on the BIOS flash, it's permitted to automatically always execute. Now this actually isn't a bad thing because it's relied upon that the assigned firmware updates have validated everything that's on the BIOS flash. So always execute is generally okay. However, for the other boot locations mentioned here, option ROM, removable media, and fixed media, secure boot will determine what to do with those based on the policy that it retrieves from storage on the flash, and we'll talk about where those are located. And then the default policy is to deny execute on security violation, which means secure boot will automatically check and authenticate everything else that doesn't fit in one of these case statements. So what we see here, this is the disassembly of the secure boot policy initialization. This is of a Dell E6430 BIOS revision A12, just for reference, much actually like this system that I have right here. What we see here, it's a little bit messy, but we see that the secure boot policy is defined by it's defined by the setup variable if the variable exists and if it's valid, in which case the contents of that setup variable are what defines a secure boot policy. Otherwise, then the results are just, the policy is just hard-coded. Now, the EFI variables themselves, which is where the secure boot policy is stored, one of these variables, they're typically stored on the BIOS flash. That BIOS flash is the same BIOS flash that contains the BIOS executable code, which executes on boot. So here we have the UEFI setup variable, and we can also see its attributes. This is this setup variable from that same Dell laptop. So here we have NV, which means it's located on non-volatile storage, meaning it's located on the flash. The BS here is, we don't really care about that, but that means that this variable can be modified from the boot services. It's really just a requirement for the RT here, which is the one we really care about. RT means this variable can be updated or modified from within the operating system. So it's accessible by what's called the runtime services in a UEFI world. So what's missing is some attribute that requires that any application that wants to modify this variable be an authenticated application. But as a result of that, I can show you a few attacks against secureboot. So as of Windows 8, Microsoft provides an API for interacting with these variables. Get firmware environment variable, set firmware environment variable are just two of those. There are others as well. So the first attack is pretty obvious since there's no authentication required. We can simply, first let me explain what we're looking at here. This is the setup variable again, just a little bit further down. This is the secure boot on and off byte. So on is 1, so secure boot is enabled, and if this were to be 0, it would be off. Here is the secure boot policy byte that refers to the firmware flash origin. So in other words, this 0 means always execute, and these remaining 4s mean always deny execute on security violation. So these would be for the fixed media, the CD-ROM, and USB, I think was the other one. So as a result, though, because this variable is accessible from within the operating system, we can modify the firmware environment variable just using the API with just a little bit of privilege required to do so. So we can use it to set the secure boot policy to always execute regardless of the origin of the media of the file that's trying to load and execute. So as a result, even though secure boot in this case is still enabled because we didn't actually disable it, it's effectively disabled, however, because it's permitting everything, so it's not really doing its job that you think it's doing. So things like bootkits or drivers or malicious option ROMs or anything really can just execute without any verification whatsoever. So in summary, this one's a little more stealthy, but this one is exploitable from userland to disable the secure boot policy, or effectively disable it, I should say, or make it permissive, really, I guess is the right way to say it. Bootkits will function unimpeded, and secure boot, however, will still report itself as running and functional. Thus, this is why I say this is a more stealthy attack. This next one is a little bit clumsy, but this is just something that we tried out to see what would happen. So we tried deleting the setup variable. Well, when you delete the setup variable in UEFI world, it reverts the system to what's called like a legacy, I guess legacy boot mode. So in other words, secure boot is effectively disabled because of that. And thus bootkits and such can also execute because secure boot is also disabled. However, when you go to check to see if secure boot is running, it will say it's not running, and so it's not exactly a stealthy implementation, but it is exploitable from userland just like the other. And again, bootkits will execute without any authentication. So the third one is really just kind of an offshoot of the second one, because we found out that when we do this, despite secure boot being disabled from the OS, when we do the actual reboot, the UEFI firmware, before secure boot is even part of the picture, detects that the setup variable is gone. And so what it does is it restores the contents of that setup variable from another variable called Std Defaults. Now, Std Defaults unfortunately suffers from the same malaise as does the setup variable. It's located on the non-volatile flash. That's not really a problem. Boot services, who cares? but it is still available from the runtime services without any authentication whatsoever. So if you're going to modify the contents of your setup variable, well, you may as well also modify the contents of the standard defaults, and thus you have a little more persistence in your making your secure boot policy more permissive, or someone else's secure boot policy more permissive. How this is fixed is actually pretty simple. EFI, in their specifications, they provide other additional attributes which can be applied to variables. One of these being an authenticated write access, meaning that the application that wants to update or modify this variable must be authenticated and signed by a trusted key located in one of the key store variables, which I'll talk about in a little bit. There's actually another authenticated access attribute that also that's set with a timestamp, so it's also called timing-based authenticated write access, but this is adequate in what we usually see most of the time. The summary of this vulnerability is we co-reported this with Intel. The cert number is here, and basically it summarizes this vulnerability allows bypass of secure boot on many systems. That's something to keep in mind because it's not strictly resolved to just Dell or this model. In fact, we first identified this vulnerability on a Dell E6430, but it's not limited to the Dell E6430. In fact, it's not limited to Dell as an OEM. It's across other additional OEMs as well. And if we looked into the UEFI reference specification, also called Tiano Core, if you will, and we looked into that, and this vulnerability is not existent in there as well. They lock these variables down properly too. So which means that someone took the reference specification and at some point unlocked them and didn't remember to lock them down again, or I should say require authentication to modify them. So that leaves basically one party who is responsible for this. And that would be the independent BIOS vendors, or IBVs. These are the guys like American Megatrends, Inside, Phoenix. They're the ones they download and take the reference specification, and then they modify it, they add a lot of proprietary stuff, and then they sell it to the OEMs like Dell, HP, and all the rest. So specifically, who did it? Well, it doesn't appear in the reference specification. Vulnerability affects multiple OEMs, so it's not Dell, it's not one of the OEMs. They don't sell to each other, they're competitors. The vulnerability was introduced by an IBV. Based on our analysis, it was AMI. So we've seen how EFI variables that are trivially writable without requiring authentication can be abused by an attacker. Now, not all EFI variables, of course, are non-authenticated. Some of them require knowledge of a private key in order to be modified. Authenticated variables such as this store very important information of the system regarding secure boot and other aspects of the system too. For example, like there's the key store that basically contains a list of a white list of hashes of applications and drivers which are permitted to execute. There's also a blacklist in there, and then there's a list of authorized keys which additionally applications attempting to load and execute are allowed to be signed by. And just to reiterate, these authenticated variables on the SPI flash are located basically just alongside the BIOS firmware executable, which actually raises a bit of a problem for the vendors. And by vendors in this case, I really mean the OEMs, the Dells and the HPs and such. So basically what it boils down to is that the SPI flash, or the BIOS flash, just for simplicity, is getting pretty crowded. And it's getting harder and harder to manage all the writability requirements of these variables. I mean, you have the BIOS executable, which during runtime should never change. So that should be read-only. But then you have these variables which, per UEFI spec, must be writable during runtime. They must be. Sometimes the operating system, some of them are arbitrary and not that important, but some of them are important, but they all have to be writable from the operating system during runtime. So the question is, how can OEMs securely implement all these different read-write permissions of these co-located all these co-located components, all these variables alongside the BIOS executable. So Intel does provide some protection mechanisms there, which can help. They provide a number of protections that can help lock down the SPI flash. They can be summarized into two basic groups, two basic entities, really. There's global write protection, and then there's range write protection. And it's up to the OEMs to implement these. So we'll talk about the global write protection first. This is all managed by the, this thing's legacy. It's been around for years and talked about for years, but it's called the BIOS Control Register. What it does, in a nutshell, is it provides system management mode the ability to control the writability of the SPI flash. So what happens here is you have two bits. You have the BIOS lock enable and the BIOS write enable. The only way the BIOS flash can be written to is if that BIOS write enable is asserted to 1. So that's all fine and dandy. But then there's the BIOS lock enable. That, when it's asserted, it can't be deasserted until the next reboot. But when it's asserted, that means that when the BIOS write enable bit is also asserted, and those two bits are both asserted together, that triggers or generates a system management interrupt. Now, a system management interrupt is one that transitions the CPU processor from protected mode or whatever, or long mode or whatever it was in before, into system management mode. That means all of their running processes are suspended. The system enters system management mode, executes the SMI handler in that secure memory space, and then resumes back, and then the processes that were suspended are resumed again after that. Now, during this time in system management mode, in this case, however, one of those checks that it does as part of its normal routine is to take a look at this BIOS write enable bit. If it sees that it's asserted, and it knows that it did not actually initiate this write to the BIOS flash, it knows it should not be allowed, and it deasserts this bit back to 0. So when the processor resumes back to protected mode, the offending application that was trying to assert this bit here sees it at 0, and for all effects, it thinks it's actually a read-only bit. But it is actually read-write. So here's just to a step through the process, kind of. So we have the attacker process here running as ring 0 because it requires either port I/O or the ability to map memory. So we have BIOS control here with BIOS lock enabled, set to 1, so that when the attacker flips this bit to 1 to make the BIOS flash writable, generates a system management interrupt. The CPU transitions to system management mode. BIOS write enable is reset back to 0, and the system resumes back to the attacker's code, or any application for that matter that attempts to set BIOS write enable with the BIOS lock enable set. And thus the BIOS remains read-only. Now, it's important to note that the only way in and out of system management mode is through a system management interrupt. I should say the only way into system management mode is via SMI system management interrupt. The only way out of system management mode is via the resume function, instruction, but that's kind of beyond the point. So now we'll talk about the second protection mechanism provided by Intel. Just very briefly, it's called the protected range registers. These basically enable the BIOS the ability to program protected range of the flash and make it write protect a range of the flash. And you can actually also set read protection too, deny reads. But write protection is the most practical. And then to lock it all down, because as we notice, looking at these here, these registers are always read-writable. Well, you have to be able to lock them down, otherwise someone could just remove your protected ranges. So there's this other register, the sequencing registers, it's F lockdown, just flash lockdown, and that once set, so once you have all your protected ranges set, then you can set F lockdown, and those protected ranges can no longer be modified until the next reboot. So the challenge is, just to restate the challenge for the OEMs, is that what it boils down to is that the EFI variable region must be writable. So therefore, it can't use those protected range registers. It has to rely solely on system management mode to protect that range of those variables, which is all fine and dandy as long as system management mode can always run and reset the BIOS flash to keep the flash read-only. However, we found that you can actually suppress system management interrupts, which effectively bypasses any and all protection mechanisms offered to you by system management mode, from within system management mode. This bypasses those BIOS control protections of the flash that I just talked about. It does not require anything other than just a little bit of privileges executing from the operating system. You don't have to execute any code or anything like that from system management mode. You can do this right from your OS and suppress SMI. So how to do this is via the SMI enables control register. It's located in the power management registers of the chipset. This is just the global SMI enable. This disables all different types of system management interrupts. However, it's part of a larger register that contains other bits that can be set to disable specific kinds of interrupts if you want to go fine-tune which SMIs you allow and disallow. But the point is I'm showing you the global one because it disables all system management interrupts. So if this register is not locked, by asserting what I'll show you later is the SMI lock bit, and when I show you how to prevent this, SMIs are disabled. With SMI suppressed, we are allowed to write to that variable region of the flash and effectively bypass or just disable the protections provided by the BIOS control and system management mode. As a side note, we've been surveying a lot of machines like throughout our company and a couple other organizations, and 40% of the systems surveyed do not have this bit set. And there's another note here which says you can also technically downgrade most BIOSes too, depending on whether they're signed or not or whether their baseline signature is. And then you can also, even if so in other words, if a BIOS has been patched and has resolved this, if you downgrade the BIOS, you might also be able to re-enable this vulnerability on the system. So this is how it works when SMIs have been disabled. So again, the attacker is trying to set BIOS write enable. It's important to note that BIOS lock enable is still set. The attacker flips bit 1 of the BIOS, well, it flips BIOS write enable, thus the SPI flash is now enabled. What would normally happen, of course, is a system would transition to system management mode, and that bit would be deasserted, and then the attacker wouldn't be able to do a thing with it. However, because SMIs are suppressed, the system never transitions to system management mode, and that BIOS write enable bit stays asserted, and the attacker is now free to modify any portion of the BIOS that he can. One thing I did mention earlier about the protected range registers. With protected range registers in place, those don't rely on system management mode, so technically protected range registers will still prevent writes to the flash. But as we know from what I was saying earlier, that the variables at a minimum must be writable. So you can't use the protected range registers on those, and there's not much you can do to protect them in this case. So these variables, like the setup variable, which contain and define the secureboot authentication settings, can now be modified and thus allow trivial bypass of secureboot, kind of like what we were doing when we were modifying the setup variable earlier. It's all pretty easy stuff. I have a demo video to show you. Okay, so what we're doing is we're just going to demonstrate, this is a UEFI system, this is the UEFI shell. Basically it's like a just command line interface. From here you can go into various file systems that the system is loaded, and you can execute things like like your bootloader and such to boot into Windows and whatever. What we're going to do is we're going to attempt to load a shim bootloader, which is the attacker's bootloader. It's one that, it's a bootkit basically. Benign bootkit, but it's a bootkit, I guess. So now what we're showing you here is that, excuse me. Okay, so earlier I had mentioned those authenticated variables. These are the ones that contain, like, say, the white list of hashes. This is the white list here. The DB is The DB database is the whitelist of hashes. So in other words, if you have if you take a hash of like an EFI drive or something like that and put that hash in here, that will be permitted to execute. We're just showing you the B and A's are just set there to just to show you that when we add a new one, it will be very visible. So those are currently the permitted drivers. So now we're just going to boot into the legitimate operating system. So right here we're using flash ROM to dump the BIOS flash. Just has a lot of output. Let's see, some of this output is important. Okay, so here just as a warning to show that attempting to write to the flash earlier, it kind of went by quick, but this is the BIOS control register. It's located offset DC in what's called the low pin count PCI device. Just a legacy device, been there for a long time, but it's offset DC is that BIOS control register. I just lost it on here. It's been disabled. So in other words, the value of that, so what it's saying in a nutshell is that BIOS lock is enabled and system management RAM has reset BIOS write enable back to 0 so that we can't write to it. So what we are doing is we're going to disable SMIs in the method I said. We just have a little script that does that. We just deassert the SMI enable bit 0 in the power core there. I was ahead of the video, but it's failed because BIOS lock enable is set. My colleague who put this together called it Charizard. I had to look it up to see what that was. So what we're doing now is we're actually able to flash the BIOS, and what we've done, and I'm going to show you in a moment, but I'll just project it here, is basically by writing to the flash, we took the hash of our shim bootloader and added it to the DB whitelist. So we expect that it should now be able to boot. So go back into the approved. We're only going into delete because that's the only way to actually list them all. But so now we see the additional. These are GUIDs. It's just how UEFI names objects and such. But we see the new addition added to the whitelist. So now we can boot to the shell, and we can again try to boot and load. To load our shim x64, which, as you'll see, like I said, my colleague wrote this, is juvenile. You'll see in a moment. There it is. So it's actually surprisingly easy to do. It's also easy to prevent, but no one seems to know about it. So it is very possible to pull off and prevent system management RAM from being able to protect your BIOS flash. If you're interested in learning how to lock it down, there's actually a couple ways you can do it. For starters, I mentioned earlier, there's the SMI lock bit. It's located in what's called the Gen Power Management Configuration Register, also located in that core area where the other ones were. It's basically containing that register contains a bit called SMI lock that when it's set, all the contents of that SMI enable register are locked in place. So what the strategy should be then is that once system management RAM is configured by the BIOS, and that once it's all set and ready to go, that they have to ensure that SMIs are configured, ready to go, and then assert this bit to prevent any further changes to it, like someone who wants to suppress system management interrupts. And then the second way to prevent this is through a newer bit that was added also to the BIOS control register. That's the one that I was talking about earlier that lets SMRAM decide who and what gets to write to the flash. This bit is relatively new. I guess it's a few years old, so I won't call it new, but it's SMM BWT, BIOS Write Protect, or BIOS Write Disable. I guess P is for disable. What it says basically is that the SPI flash cannot be written to unless all cores of the CPU are in system management mode. So even if, what that means is that if this bit were asserted, thus requiring the processor and all its cores to be in system management mode before the BIOS flash could be written to, even if you did suppress system management interrupts and then assert BIOS write enable in the BIOS control register so that you could modify the SPI flash, you can't modify it at all because the CPU will never enter system management mode. So it's kind of a nifty little chess move here. This bit should pretty much always be set. But again, most vendors do not, as you'll see from our research results coming up. So the current state of protection is less than great. Over 10,000 systems so far we've evaluated, and only literally 6 of them have actually had the SMM BIOS Write Protect bit set, BIOS Write Disable bit set. About 40% of the systems measured, as I said earlier, did not have the SMI lock set. That might be a typo. It might have SMI lock set. So more vendors, and this is really the responsibility of the OEMs, but the OEMs really need to be aware of this and to just set their BIOSes to configure these bits to prevent trivial attacks like this. This is really easy stuff. We actually have more talks in the works coming about also other ways to bypass secure boot protections and such, but that's for another day. But these are like the easiest to do. So basically, in summary, the secure boot is a good thing for the most part. It does provide your system protection from malicious or unwanted executables from executing during the boot process, like a bootloader or something like that, or I should say a bootkit. However, it's defined by variables located on the flash that can be trivially overwritten if not secured. Those variables must require authentication to be modified. And then, of course, the underlying architecture underneath that in the chipset must also be configured so that the system's most important resources, like system management mode, can actually do their job and protect your system from malicious writes to the flash. Here's just a list of some related work we've been working on as well: a Tale of One software bypass of Windows 8, secure boot, and defeating signed BIOS enforcement tools. And just some acknowledgements too. Rick Martinez is actually with Dell. We did disclose all of this to them prior to ever releasing it and such, of course. Actually, I feel like I finished very quickly. Must be speaking very quickly. But does anyone have any questions? Maybe not really. Thank you.